Hello, my dear students in grade 9. Today we're making our revision on February month. In this revision, we'll cover the informations that we have learned during this our study. So it'll be like a fast revision with details, but we will not solve problems because we did that already. Okay. Now this first lesson speak about the energy, and it's like the basic concepts in our thermochemistry unit. Okay, that's great. So as we know that energy, what is energy? It's the ability to do work, to do work, the ability to do work. So we can divide the energy into two main types: kinetic energy and the potential energy. The kinetic energy is the form of energy it combines with motion, and the potential energy it combines with static phase or static state, like no motion. So here, for example, or from the examples of the kinetic energy, we have the heat energy, which we are calling sometimes the thermal energy. So heat energy is the thermal energy. And the definition of thermal energy is not in our content, but we must know and understand to be able to go further in our study. So thermochemistry is a form of kinetic energy, kinetic or kinetic energy, which is a type of or form of kinetic energy accompanied with random motion of the particles. So as you know, any matter consists of molecules, and the molecules consist of atoms. These particles are in continuous motion. So thermal energy is a form of kinetic energy accompanied, which is associated with a motion, random motion. It's not a unified, it's a random motion. And we will see later that we're using the word average speed to refer to the motion of the particles because it's a random. It differs from particle to another in the same body. Okay, that's great. So the heat energy or thermal energy is a form of kinetic energy accompanied with like a random motion. On the other hand, from the potential energies, we have the chemical energy. Chemical energy is stored in the bonds between the atoms or between the molecules in the form of the potential energy. That's great. There are several other or many more forms of the energies. For example, the light energy, which we sometimes call the photonic energy. There is the electrical energy, the sound energy, and several more. Okay, that's great. The link between these energies, we're using a law. It's essential or fundamental law in the science. It's called the law of conservation of energy. It's a fundamental law. So this law says that the energy cannot be created nor destroyed, but it changes from form to another. As you can see here, it says that energy in any physical or chemical change cannot, or it can be neither created or destroyed. So it can't be created or destroyed, but it transfers from one form to another. This is the law of conservation of energy. Remember with me that you in the last semester you have got another fundamental law, the second one, that is similar with this. It has some similarity between them. The the law that you have got in your first semester is the law of conservation of mass, which says that mass cannot be created nor destroyed, but transfer from one form to another. Here we're talking about the conservation of energy, and it's the same way. Energy cannot be created nor destroyed, but change from one form to another. That's great. So again, let's go back to thermal energy. Thermal energy, as we said, is a kind of kinetic energy accompanied with a random motion of the particles. This energy can transfer from a body to another. But how? To transfer the energy, to transfer this thermal energy, it transfers from the higher temperature body, higher temperature, the body with higher temperature, or the object that has higher temperature, to the body that has lower temperature. But how does it happen? How does it happen? Actually, it happens in the form of quantity of heat. Okay, so the thermal energy transfers from the higher temperature body to the lower temperature body in the form of quantity of heat. That's great. So heat, the quantity of heat, is the amount of thermal energy transferred from the higher temperature body to the lower temperature body. As we have a difference in the temperatures, we can find or can see heat transfers. Okay, but if we don't have any change or any difference in the temperatures between the two bodies, then there is no transfer of the thermal energy. So this is the only conditions that controls the transfer of energy. It transfers from the higher temperature body to the lower temperature body in the form of quantity of heat. And we can say that the quantity of heat is the amount of energy transferred from the higher temperature object to the lower temperature object. That's great. But what is the temperature? Temperature is the measurement of the thermal energy, which is thermal energy is a kinetic motion, right? It's a kinetic energy, so which is the motion. Let's change the color of the pencil here, or the pen here, to see it. Okay, so it's a measurement. The temperature is a measurement for the thermal energy, which is a motion for the motion or the movement of the particles. As I told you before, any particle is in continuous motion. So if you measure this motion, then you're measuring the temperature, because temperature is the measurement for this motion. And we are calling it, or we are using the average motion of the particles. So temperature is the measurement for the average motion of the particles. So we're using here the word average before the motion, because as I told you, thermal energy combined with a random motion. This random motion means that these particles has different speeds, and the speed, because it's different, it's better to use the average speed. Use the word average to express this speed, because these particles are in the same body but move with different speeds, have different speeds of the vibration or the motion, so we're using the average. That's great. So now we have got the concept of the heat, which is the amount of energy transferred from the higher temperature body to the lower, and we got the definition of the temperature with the measurement for the average speed of the particles in the body. That's great. So let's go here, and this is a relation between the kinetic energy and temperature. Temperature measures the motion, right? That's great. So if a body here absorbs energy, this body absorbs energy. Okay, so its kinetic energy will increase. The kinetic energy will increase because it absorbed energy, so the motion also will increase. And the other result, the temperature which measures the motion also will increase. Great, that's good. So there is a direct relationship between the kinetic energy and the temperature. We're measuring temperature with Celsius in our text box here, and there's other units like Fahrenheit and the Kelvin, but we don't use it in our textbook. That's great. That's great. Okay, so here we can say so the temperature is an indication for the coldness and hotness. We can use the temperature to see or to express whether this object is hot or cold. Okay, so it's an indication for the coldness or hotness. Let's go for some basic concepts in our thermochemistry content. In thermochemistry, before speaking about what is thermochemistry and what are the important concepts and the ideas in thermochemistry, let's speak about what made thermochemistry. Thermochemistry actually is the result of the integration between thermodynamic and the chemistry. So thermodynamics integrates with chemistry to form thermochemistry. What is thermodynamic? Thermodynamic is the branch of science that studies or deals with the study of energy. So it studies energy. And as it's dynamics, thermodynamic, it's also studying the transfer of this energy. So thermodynamics as a science deals with the study of energy and how it transfers. It studies the energy and how it transfers. So when thermodynamic integrates with chemistry, we are saying that we have a new branch of science is called thermochemistry. Thermochemistry is a branch of thermodynamic concerned with studying the heat exchange. It is concerned with studying the heat exchange, as we saw in this month. We speak about different types of heat exchange. We speak about the enthalpy or the heat content. We discussed the heat of solution, the heat of the dilution, the heat of combustion, the heat of formation. So there are several forms of the heat. So thermochemistry studies the heat exchange, which heat exchange that accompany the chemical exchange, accompany the chemical exchange and the physical exchange too. For the examples on the chemical exchange, the combustion and the formation and from the examples on the physical is the solution, the heat of solution. So we are saying that this will change the dissolving process. When dissolving something, we are making a physical change, and also the dilution which make the concentration of a solution turn from higher concentration to lower concentration. It's the dilution process, and we discussed it also this month. That's great. So we now know that what is thermochemistry and what is thermodynamic. That's great. Fine. Thermochemistry studies the heat exchange, but where do we study this heat exchange? Actually, we're studying the heat exchange in something called system. So the system is the part of the universe in which the chemical exchange and the physical exchange happens. So this part of the universe includes the physical exchange and the chemical exchange. This is the system. System has boundaries. Any system has boundaries. Boundaries are the layers, Boundaries are the walls of the ends of the system. It's the end of our system, and they can be real, can be touched. They are real, have a body, or we can imagine them to be imaginary for some cases. Anyway, we don't have any information about boundaries in our context, but let's make sure that boundaries express or refer to the end of our system. Outside the system, there is something called the surrounding, and from its name, it's all the parts surround the system. It's the rest of the universe, because the part of the universe under study is the system, so the other parts which we don't study are the surrounding. And actually, surrounding and the system are in contact. They can exchange energies, they can exchange matter, or they can change both of them. The surrounding and the system can change matter or energy or both. If our system and surrounding exchange both the energy and mass, we're calling it an open system. Open system here. And if it exchanges only the energy, it's a closed system. But if they don't exchange energy nor matter, this is an isolated system. So we have three types of systems according to what the system and surround exchange with each other. If they exchange both matter and energy, this system is an open system. And if these are exchanging with each other just the energy, this is a closed system. While if they neither exchange neither energy nor matter, it's an isolated system. And our study through this thermochemistry content, we're speaking about the isolated systems because as we'll see here, there is a law. It's called the first law of thermodynamics. The first law of thermodynamics says that the total energy of any isolated system is constant even if the system is changed or it changes from a state to another. So the total energy, the important part here, is the total energy of any isolated system is constant. So during our study in the thermochemistry, we are studying the heat change in isolated system because we can control both the matter and the energy. Okay, let's give some examples on the open system. The open system is such as the cup of tea, for example, and or the human body. Our bodies exchange matter and the heat with the surrounding, with the environment around us. The closed system, for example, we have the thermometer, which the doctors use. So thermometer is a closed system because it exchanges energy only. So when we are using the thermometer, we put this under our tongue to measure our temperature, the temperature of our body, by transferring the heat from or the thermal energy from our body, which is have higher temperature, to the thermometer, which had a lower temperature. When the thermal energy transfers from our body to the thermometer, the motion of the particles of mercury, which existed inside the thermometer, started to increase. So this motion makes the mercury expands and they give us a read that mentioned or refer to our body's temperature. That's it, great. Another form or another example on the closed system is if we got this open system example, which is the cup of tea, and they covered this cup of tea. If we covered the hot cup of tea, this cup of tea will lose heat but won't lose the vapor of water, which is a matter. So the covered cup of tea is a closed system. The last type of systems is the isolated system, and here we are using examples like the thermos. Thermos is like a container we're using to save our hot beverages hot and keep it for long times and keep the temperature for a long time. Okay, store it hot, keep it hot. The thermos is a container in our kitchen. We're using it, fill it with the hot beverages to keep it hot for a long time. And also there is a very important application of the isolated system is called the calorimeter, or we're calling it calorimeters. Calorimeter Calorimeter or calorimeter is like a device used to determine or to measure the quantity of heat the quantity of heat transfers directly in the term of the change in the temperature. Okay, we'll discuss it in the last part of this lecture. Now let's go to the first law of thermodynamics again. The first law of thermodynamics said that the total energy of an isolated system is constant whether or if even if the system it changes from a state to another. And we have to notice something very important. If we're studying our system and we discovered or noticed that our system lost energy, this amount of energy will be gained by the surrounding. So if our system lost energy, the surrounding will gain this energy. Okay, that's great. So as you can see here, if our system loses energy, lose have a negative sign, the surrounding will gain positive add, so it's positive energy. That's great. From this part, we can say that the change in the system energy is accompanied by change in the surrounding energy too. So any change happened to the system energy, it accompanies or accompanied by change in the surrounding energy. This change is similar in the value but opposite in the sign. Same value, opposite sign. The negative sign refers to loss. The positive sign refers to gain. So here positive means gained, negative means lost. Okay, so if the system gained energy, the surrounding will lose. And also we can say that if our system, if the energy transferred from the system, this energy, this thermal energy will transfer in the form of quantity of heat from the system. So if the system lost energy, then the heat will transfer from the system, like quantity of heat, to the surrounding. So our system here lost quantity of heat, and the surrounding will gain this quantity of heat. Okay. So what is quantity of heat? The quantity of heat is the amount of energy transfers from the higher temperature body to the lower temperature body. What are the units used to measure the quantity of heat? We're using here the calorie and also the joule. Calorie and the joule. Joule is the SI system, SI unit, and the calorie is the common unit which we were using last in the previous, but now we're using the joule. Okay, so what is calorie and what is joule? Calorie, as we said in our class, it's the father of the joule. It's the greater unit, and the joule is the smaller unit. So to transfer, or sorry, to convert from the calorie to the joule, from the greater to the smaller, we are multiplying. And from the smaller to the greater, we are dividing. But what if the numerical values that we're multiplying, or what if the numerical value that we are dividing by? Actually, to know that, we have to see the definitions of each one. Calorie is the amount of energy, is the amount of heat or of energy, or the quantity of heat, anyway, required means needed, to raise the temperature, of 1 gram of pure water. 1 gram of pure water means clean water, H2O, only water, by 1 Celsius degree, from 15 Celsius to 16 Celsius. The amount of energy raises the temperature of 1 gram of water from 15 to 16 is the calorie. And to transfer it, the joule is the amount of heat required to increase or to raise the temperature of 1 gram of pure water. This is the same up here. We're saying the same words here. We're increasing the temperature of 1 gram of pure water by 1 divided by 4.18 Celsius degree. So 1 joule increases the temperature of 1 gram of pure water by 1 over 4.18 Celsius degrees. So as you can see here, 1 calorie raises temperature 1 Celsius degree, while the 1 joule increases it by 1 over 4.18 Celsius. So joule is smaller. To transfer from the calorie to the joule, we are multiplying by 4.18, and from joule to calorie, we're dividing by 4.18. Remember this definition because we will use it to define or to discuss something is called the specific heat. The specific heat. Okay, let's go. What is the specific heat? It's the amount. Okay, let's see it. Let's see directly while we are writing it, while we have it here. So here again, the specific heat is the quantity of heat required to raise the temperature of 1 gram of, notice that the first difference here is to increase the temperature of 1 gram of any substance of the substance by 1 Celsius degree. So let's see here, let's compare between the specific heat and the calorie. Calorie is the amount of heat needed to raise the temperature of 1 gram of pure water. The substance here is water. While here in the specific heat is the amount of energy needed to raise up the temperature of 1 gram of the substance, any substance. So this is the difference between the specific heat and the calorie. By 1 degree is the same. Okay. So if we changed any substance and put water, can you tell me what is the specific heat of this water? Sure, because they have the same definition. The specific heat of water equals 1 calorie per gram Celsius. So 1 calorie per gram Celsius is the specific heat of water. Again, the calorie is the amount of heat required to increase the temperature of 1 gram of pure water by 1 Celsius. And here, if we're talking about specific heat, it's the amount of energy required to increase the temperature of 1 gram of any substance by 1 Celsius degree. And here, if we change it any substance by water, then we're talking about the specific heat of water. So specific heat of water equals 1 calorie, because 1 calorie is the amount of heat required to increase the temperature of 1 gram of the pure water by 1 Celsius. So it's the specific heat. But the difference here is that specific heat has a unit is 1 calorie per gram Celsius. So we're measuring the specific heat by calorie per gram Celsius. If I asked you, can I use joule per gram Celsius? Surely your answer will be yes, you can use also joule per gram Celsius. As I told you, joule is the son of calorie. Calorie is the father. So if I could use calorie, then why not joule? Okay, but make sure to transfer. So 1 calorie of the specific heat of water equals 4.18 joule per gram Celsius for water. So water had specific heat 4.18 or 1 calorie here, 4.18 joule per gram Celsius or 1 calorie joule Celsius. That's the point here. But let's discuss the characteristics or the properties of the specific heat. A specific heat, as you can understand from its name, the specific means it's a specific heat. So let's notice that the specific heat is characteristic. Characteristics property So it's specific or characteristic for the substance. That means specific heat, which has the symbol C, is it changing or it changes according to the matter, depends on the matter. It changes from one matter to another. The second thing that the specific heat depends on is the physical state. The physical state. Let me ask you something. What did we say about the specific heat of H2O, the water or the water? We said that it equals 4.18 joule per gram Celsius. That's great. But if I told you this is the specific heat of liquid water, what is the specific heat of H2O vapor, the vapor water? Here is, you'll notice the difference here. By changing the physical state, the specific heat differs. It equals 2.01 joule per gram Celsius. So again, as you noticed here, the specific heat depends on the physical state as well as the matter itself. So there is no two matters has the same specific heat because its characteristics property differs from one matter to another, and also it depends on the physical state. I'll give you a very important information here. The specific heat of water, of liquid water, is for memorizing. So you must memorize it. It equals 4.18. And if you're a smart student, you must say that I know it before because I know that the 1 calorie equals 4.18 joules. Okay, so if you know how to convert from the joule calorie to joule and the joule to calorie, you must know that the specific heat also has the same value, numerical value. That's awesome. And the important information here that I want you to know, the water had the greater or the higher specific heat of the other different substances. It has higher specific heat than the other substances. And if I told you give a reason or why the specific heat of water is greater than the other substances, you must say because it requires a higher temperature to raise the temperature. It requires a higher quantity of heat to raise the temperature of 1 gram of it 1 degree. So it requires higher quantity of heat to raise its temperature than the other substances. The answer is it requires higher quantity of heat, sorry. It requires higher quantity of heat to raise the temperature of 1 gram of it 1 degree, which is higher than the other substances, greater than that of the other substances. That's fantastic. So good. Let's speak now about the relation between the specific heat and also the time required to raise the temperature of the matter. Let's compare between two substances, then discuss what we want from this example. Here we have a cube of copper. Its specific heat equals 0.3 joule per gram Celsius. Joule per gram Celsius. And on the other hand, we have the specific heat of the ferrum is the iron, equals 0.4 joule per gram Celsius. So if we ask you the first question, which one had the higher specific heat, your answer will be the ferrum or the iron had the higher specific heat. That's good. The second question, if I told you, we have two cubes of copper and one of copper and the other of ferrum or of iron, and now we got this similar identical cubes, one of copper and the other of iron. They are of the same mass, 1 gram and 1 gram, and we applied them or put them on the flame. These flames provide the same amount of heat, the same quantity of heat, Q. Q is the abbreviation or the symbol of the quantity of heat, as we mentioned before. So here we put this identical cubes of copper and the iron on the same amount of quantity of heat. The question is, which one will get higher temperature if they were supplied for or if they were on the flames for the same time, at same time. T small means time. T capital here, the capital T means temperature. Temperature. So temperature has a capital T, and while time has smaller letter T. That's good. So which one here, from your knowing, if you know that they have the iron has higher specific heat than the copper, which one will get higher temperature at the same time? Same time, if they were on the flames for the same time. Actually, let's go back for the definition of the specific heat. It said that the specific heat is the quantity of heat requires to raise the temperature of 1 gram of the substance 1 Celsius degree. So as the specific heat increases, the quantity of heat required to raise the temperature of 1 gram of the substance 1 Celsius degree increases. The quantity of heat will increase. So if we looked here, the specific heat of iron is greater than the specific heat of the ferrum or of the copper. So which one will need higher quantity of heat? The iron. That's good. As the iron needs higher quantity of heat to raise up its temperature 1 Celsius degree, then it will take longer time. It will take a longer time to raise it 1 Celsius degree. Longer time. So if we are measuring them in a specific point of time, like after 5 minutes, we'll find that the temperature of the copper is greater or higher. The temperature of the copper is higher than the iron. So as the specific heat increase, the quantity of heat required to increase the temperature 1 Celsius degree increase, and also the time increase. That's why if we're comparing between two substances, the one with the lower specific heat need lower quantity of heat, so its temperature raises faster. The lower specific heat raises its temperature faster. So the copper here will get higher temperature in a shorter time. Okay, I hope you understood this part because it's very important. And there are a lot of questions in exams about this part. Okay, so when the specific heat of the substance is high, the quantity of heat required to raise the temperature of 1 gram of the substance 1 Celsius degree is high, and the vice versa means when it's low, the quantity of heat low, and also the time when it's high is long, and when it's low, it's short. That's great. Let's calculate now the quantity of heat. I'll say I won't measure the quantity of heat with you now, because I will measure the quantity of heat and the specific heat and also the mass. And if we want, we will measure also the delta T, which is the change in temperature too. Let's see here, what should I do to measure the quantity of heat? I have a law say that the quantity of heat equals the mass of the substance, or if it's a solution, it's the mass of the solution. Okay, multiplied by C. C is the specific heat of the substance, and if it's a solution, then it's the specific heat of the solvent. Multiplied by delta T, which is the change in the temperature, and any change equals the saying after the change, before the thing, subtracted the thing before change. So it equals T2 subtracted T1, means the T after the change or the transfer of heat subtracted before the transformation of heat. Okay, or we can call it the final temperature, and here it's the initial temperature. The change in temperature equals the T2 subtracted T1, and we're measuring it by Celsius. Okay, good. Now, to calculate the quantity of heat, we must know that the mass of the solvent, of the substances or the solution, the specific heat of the substance or the solvent, the change in temperature. Sometimes in the problems, we don't get the mass. We don't get 5 grams, for example, but we get 5 milliliters. We must know that it can be equals the mass of the solution, and the mass of the solution equals its volume. So 5 milliliters equals 5 grams, although 5 cubic centimeters equals 5 grams. So we remove milliliter and provide gram. So we are measuring the mass by the unit gram, So make sure that if you don't know the mass, you must look at the volumes and change the unit of the volume to the unit of the mass. Here, the specific heat, sometimes we don't get it. If he didn't give it to you in the givens of the problem, then he says for you it's the specific heat that you memorized. And luckily, we have one only specific heat to memorize, which is the specific heat of the water, which is 4.18 joule per gram Celsius, or 1 calorie per gram Celsius for water. So it's specific heat of water. Or a solution, its solvent is water. The solvent in it is the water. Okay, great. Let's measure the specific heat now. Let's try to measure the specific heat. A specific heat equals the quantity of heat divided by the mass multiplied the change in the temperature. Let's measure the mass. The mass equals the quantity of heat divided by the specific heat, and the change in temperature multiply the change in temperature. Also, let's measure the change in temperature. Okay, the change in temperature equals T2 subtracted T1. If he gave you T2 and T1, then the T final and T initial, you will make this a rule or this law and substitute in here and get the result of the change in temperature. If he didn't give you the initial and the final temperatures, then you will use this form too, but by making an operation here, like making it like equals Q subtracted MC. It's not a big problem. Sometimes he come after that and tell you, give me T2. So T2 you can measure after getting delta T. You can substitute here by knowing T1 and solve again and get the T2 to say T2 equals the change in temperature plus T1, or you can say that T2 equals Q divided by MC plus T1. T2 here. Okay, and the same if he wanted T1, you can say that T1 equals minus Q by MC plus T2. Okay, good. Now let's go for the last part of our lecture today, which is the calorimeter or the calorimeters. Calorimeter or calorimeter is a device used to measure the quantity of heat directly by in the term of the change in the temperature, by knowing the change in the temperature, the T initial and T final. This device consists of simple parts. Here is the simple calorimeter, or the coffee cup calorimeter. It consists of thermometer to measure the change in temperature, a stirrer to move the solution or the reactants inside this calorimeter to make the temperature unified in each part of the solution. Here is the container, which is an isolated cup, isolated to make no exchange of heat or matter with the surrounding. And here is the stopper to close our system, to make it isolated. Okay. Now, if the reaction happens and the calorimeter had explosion or explosive reaction, it's better to use a suitable device that can handle this huge amount of released energy. We're using a kind of calorimeters. It's called the bomb calorimeter. It's made of steel and has special items added to help it do or perform these reactions in the very good way or correctly. It consists of the ignition chamber, because this is a reaction combustion or something, so it's an ignition container or chamber. Inside it we have our sample and the source of oxygen, because any combustion reaction, any burn requires oxygen. So we have the sample here inside the ignition container, which is made of steel actually, and you know that steel can exchange energy. As you can see here, the energy transfers from inside the ignition container out to outside the surrounding, which is water here, and this water actually is called the heat transferring fluid, or the heat, we can call it heat exchange liquid. Okay, we're using water because it has high specific heat. That means it can get or requires it can absorb high amount or high quantity of energy to raise its temperature. So it can absorb high amounts of energy. So we're using it as a liquid exchange, heat exchange liquid. Okay, we have here like an ignition wires inserted from outside to inside this ignition container to release an ignition or like a spark. This spark starts or initiate our combustion reaction, our reaction. This reaction will release the energy inside the ignition container. It will be transferred from the ignition container outside to the liquid exchange, the heat liquid exchange, the heat transferring fluid or the heat exchange liquid, which is water. This water will get this heat, and the thermometer here will read the change in the temperature. And also we have the stir, but here it has a motor. This motor made to make it easier to unify the temperature inside this container or this bomb calorimeter. Okay, and in the same way it can hold it can determine the quantity of heat in the term of the change in temperature, but the difference here, it can handle high amounts of released energies of the explosive reactions. Okay, that was our first lesson here. I hope you understood it. This was our first revision lecture. I'll meet you in the next video. I hope you're studying well. If you have any questions, don't hesitate chatting with me on WhatsApp. See you soon. Bye.